hello everyone for your welcome to the talk about elliptic curves. So nice that so many of you tuned in. Okay, so I don't know, during your maths education / contact with maths education, you've probably encountered a lot of terms that are called elliptic with no real explanation as to why they are called elliptic. And today in particular, we're going to have a look at elliptic functions, elliptic curves, and elliptic integrals. And well, we're going to have a look at the connections between them, as well as the reason why any one of them would even be called elliptic. And well, we're going to start with functions, then we're going to go to curves, and then we're going to go to integrals. And it's only the integrals that have a direct connection to actual ellipses. So I guess you will have to watch until the end to find out. Now, when you look up elliptic functions, you're going to immediately see a lot of complex analysis. And well, that is true because they are a concept from complex analysis. And in particular, they are a particular class of meromorphic functions that are characterized by their periodicity. And I guess to explain what I mean by that, I'll quickly drop a few definitions to make the notion of periodicity a bit more clear. So let f from C to, well, it's really the Riemann sphere we are going to map to, be meromorphic, or I guess we should say C to C meromorphic or C to the Riemann sphere holomorphic, but never mind. We're going to define a set called lambda of f as those numbers such that for any w and c, f of w is equal to f of w plus z. And this is called the periodicity group. So it is the set of all periods that our function has. And as the name already suggests, it is a subgroup of C with addition. And yeah, I guess this periodicity group can actually just have 4 different values, so to speak, for f as before. One of the following always holds. Firstly, this periodicity group can be all of C. Then we call f a constant function. Secondly, it can be isomorphic to the integers. Then we call f periodic or simply periodic. or singly periodic, because it has a single fundamental period. Then it can be isomorphic to Z squared. Then we call F doubly periodic. Or it can just be the trivial group, in which case we call F not periodic. Or I don't know if we call it unperiodic, but anyway. Well, so I guess a couple of comments. The constant functions are boring, or let's say we have already understood them. Secondly, singly periodic functions, we already know how to deal with them because we can expand them as a Fourier series. And so, yeah, in a way, the exponential function modified by some period factor is in a way the most fundamental one, and all of the other ones can be expanded as a power series. And unperiodic functions, I don't know, they are not for us. We are going to have a look at doubly periodic ones, or at least the most interesting cases are going to be doubly periodic ones. And this is already where we define what we mean by an elliptic function. Let lambda be a lattice, so I mean it is isomorphic to Z squared, and this is a subgroup of C with addition. So exactly like in the doubly periodic case. Jesus. A meromorphic function. F is called elliptic, or capital lambda elliptic, because why not carry that information around if lambda is a subset of lambda f. Meaning that f is either doubly periodic, with lambda being their period, although I guess it could have more periodicity. The periods could be shorter, but at least lambda has to consist of periods of that function. Or it could just be constant. And I guess one remark, we have arithmetic on meromorphic functions. We can add them, we can subtract them, we can multiply them, divide them actually. Those are operations that affect the outcome of the function and not the input, whereas periodicity affects the input. So what I'm trying to say is that they actually form a field. Form a field called E lambda or whatever. I've nowhere found some nice terminology, so I'm just making it up.
When you define pointwise quotient as, well, 0 times infinity is equal to 1. You need that convention, do you?
You actually don't define it that way. Okay. You take the limit.
Ah. Okay.
Or let's say you multiply them and then you get something that might have removable singularities, and then you just remove them.
Okay.
Yeah, another remark that sort of ties into what I said before. If a function has this periodicity, its derivative also has that periodicity. So for f in E lambda, we also have f prime in E lambda. And well, we could reinterpret things a bit. We could say elliptic functions are functions that have that periodicity. Or we could say elliptic functions, or I guess lambda elliptic functions, are meromorphic functions defined on the Riemann surface C modulo lambda. Because C is a Lie group and lambda is a discrete subgroup, so closed, so a Lie subgroup and a closed Lie subgroup. So we can take their quotient, and their quotient isn't anything group-like anymore. Oh, sorry, it is, but that's not the point. The point is that their quotient is still a manifold and works nicely with complex structure. So it is indeed a Riemann surface. And well, meromorphic functions on that Riemann surface are just meromorphic functions on C that have that periodicity. So nothing really happening here. Yeah, so I guess our goal is to find out what does the field E lambda look like. And one of the first things to note is that, well, I've already mentioned that constant functions are also elliptic. So we have that C is a subset of E lambda, or I guess alternatively that E lambda over C is a field extension. And also note that C is algebraically closed, so this field extension cannot be algebraic. It has to be transcendent, hence the transcendence degree of E lambda over C has to be at least 1. The question is it 1 or is it bigger than 1? Or to be fair, it could also be 0 and E lambda is just equal to C. We don't know yet if there are any non-constant elliptic functions at all. So our first goal is to construct a non-constant elliptic function. And for the purposes of this derivation, we choose a basis. For lambda, we write lambda as z times 2 times omega 1, direct sum z 2 times omega 3, where I guess we still have a lot of ambiguity of choosing our basis, but additionally, we are going to require that the imaginary part of the quotient of omega 3 and omega 1 is bigger than 0, which basically translates to if this is omega 1 and this is omega 3, then the quotient of the imaginary parts is positive. But if this is omega 1 and this is omega 3, it's negative. So you can just exchange them and have the, well, anyway. And also a bit of extra notation. We define P to be the fundamental parallelogram. What does that mean? Define it as the set of A times 2 omega 1 plus B times 2 omega 3, such that, well, A and B are bigger or equal than 0 and less than 1. Sort of the unit cell of the lattice that is spanned by 2 omega 1 and 2 omega 3. So if we have the lattice here, I guess this is 0, this is 2 omega 3, this is 2 omega 1, and then here we have 2 omega 2. Well, I'm going to define that a bit later. Then P is just the set that is included here, where we sort of include the left and the bottom edge and have it open on the right and on the top. This is P. And I guess one thing to note, that all of the values, or that, yeah, any elliptic function f in E lambda is determined by f restricted to that parallelogram, because you can just extend it doubly periodically and you get an elliptic function. And yeah, first thing to note, every holomorphic elliptic function is constant. Why is that? Well, holomorphic means it doesn't have any poles. So it is defined as a continuous function on the compact set closure of P. So it is bounded on that set, but since it is determined by the values it takes on P, like it is bounded on the closure of P, so it is bounded everywhere. So then we have a holomorphic function on C that is bounded. So by Liouville, it is constant. So I guess our takeaway is that any interesting elliptic function, or I guess any elliptic function we are now looking for, needs to have at least one pole. But can it actually have just one pole? No, it has to have more than one pole. That's the next lemma. Let f be an elliptic function. Then the sum of the residues on P is 0. And the proof for this one is actually quite funny. So I'm going to do it a bit.
It's also a funny statement.
Yeah, the proof is actually very easy. So I guess you assume that on the boundary of P, F has no poles. Otherwise, we can move P just a little bit, and then we would still have a unit cell, and in particular, the residues would still have the same sum. Then, well, we can integrate along P, along this boundary. So this is gamma or whatever, then the integral of f over gamma is equal to 2 pi I times that sum. But note that the function down here is actually the same as up here. So the integral along this path is the same as the integral along this path, but with a minus sign. And similar, the integral along this line is the same as the integral along this line, this line, but again with a minus sign. So the integrals cancel and you have 0. Okay, so this means if f has just one single pole, one simple pole, then, well, its residue at that pole would be non-zero. So then the sum of the residues can't be 0. So we need to have at least 2 simple poles or 1 double pole. And that's actually all we have to know. We can just do a very stupid try. I called it the stupidest try of constructing a non-constant elliptic function. I'm going to call it P for no reason whatsoever. And we define it to be 1 over z squared. So we have a double pole at 0. And, well, okay, we need it to be doubly periodic. So let's just sum over all the lattice sides. I guess we have already included 0. 1 over z minus w squared. Okay, so we have forcefully made this function doubly periodic. It has a double pole. So nice, right? Well, okay, it doesn't really converge. So let's just include some form of counter term here. I guess now it's not so clear that it's still doubly periodic, but well, when you take the derivative, then this term vanishes and you have a doubly periodic function. And now all you have to concern yourself with now is try to find out if you take the antiderivative again, you get some sort of non-periodicity, but this doesn't happen. So we've done it. Converges, non-constant lambda elliptic function. Nice. And it's called Weierstrass P function. And it has its own LaTeX symbol, so it has to be important. Also note that just by the definition, we can tell it is even. So if you plug in minus some value, you get that same value back. Now something I didn't really mention, but could have also come to that conclusion earlier. So if f is an elliptic function, then there's actually more we can say just by the number of poles that it has. So let n be the number of poles of f on P counted with multiplicities. Then f takes every value c and c exactly n times. Well, again on P and again counted with multiplicities. So why is that? Well, we have f is elliptic, constant functions are elliptic, the derivative of f is elliptic, it forms a field, so f minus c over f prime is also elliptic. So the sums of the residues is 0. But now by the argument principle, the sum of those residues are, well, the number of, I never know which direction it goes, so maybe what I'm writing down is off by a factor of -1, but it doesn't matter because we have a 0 there anyway. Is the number of poles of, well, f with multiplicities minus the number of zeros of, okay, note that this is really equal to f minus c over the derivative of f minus c, which should be a bit more, yeah, recognizable. And well, here we have the poles of f minus c, but if you adjust the function by some finite amount, like the poles are not going to change. So those are also the poles of f minus the number of zeros of f minus c with multiplicities. But now the number of zeros of f minus c are just the number, are just the frequency with which f attains the value c. So this difference is equal to 0. So of times f is equal to c with multiplicities is equal to, well, the number of poles of f with multiplicities, which is just n. And, well, that is what we set out to prove. So if we now again look at our example, we know that the Weierstrass P function has a double pole, and that's it. So it should take every value twice, well, with multiplicities. So I guess the question we could ask ourselves is, are there values that are taken doubly? So we have, since P is even, have P of z is equal to, well, due to periodicity, we can add a period. In particular, we can add sort of our fundamental periods. Note that I defined omega2 as omega1 plus omega3. And also note that, yeah, I don't know. Anyway, so we know that those two are equal. And a couple of them are always in P. Or let's say no, one of them is always in P. If our value is on, yeah, sort of usually you go for this one here. This one is usually always in P, except when Z is on one of the two axes. And then it's either this one or that one. So we know that every value is taken twice. And well, here we always have another point in P that has the same value. So unless those happen to be equal, unless Z happens to be 2 omega 1 minus Z, or 2 omega 2 minus Z, or 2 omega 3 minus Z, the value P of Z is attained twice. Or another way, or in other words, there are exactly 3 points where P has a value with multiplicity 2. Well, because in every other case, we know that it has to have multiplicity 1. And what are those 3 points? Well, the case of Z is equal to 2 omega 1 minus Z, or 2 omega 2 minus Z, or 2 omega 3 minus Z. So what are these values? Well, omega 1, omega 2, or omega 3. And this is exactly why I called them that, or why I chose the periods of our lattice to be 2 times omega 1 and 2 times omega 3. And I guess we should also come up with names for P applied to the omega I. We're going to call them eta I, but this is not going to be that important. Now our next question is the question, is there any relation between P and P prime? Or put differently, is there an ordinary differential equation that P satisfies? And well, for that, we're going to find some Laurent expansion for P. This is going to be a bit ugly. I don't know how much I'm actually going to do. Well, I guess one step is to find a Laurent expansion for the term 1 minus Z minus W squared minus 1 minus W squared. So this term that we summed over all lattice sites. And well, you can do a lot of, I don't know, a bit of geometric series, and then you find that it's equal to the sum of n equal 2 to infinity of n Z to the n minus 1 over W n plus 1. Recall that W was just a number, but Z is our variable. And we're sort of looking for a power series that converges within some circle, not outside of some circle. So we want to have the power increase. And well, then we can sort of piece everything together and get the Laurent expansion for P of Z to be 1 over Z squared plus, and then the sum over all lattice sides, all non-zero lattice sides of that expression. And well, we can sort of okay. No, this is actually 2 steps. Now we can exchange sums. Blah, 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 something, something Fubini. You know the drill. And then we have as a power series in Z. Well, we can pull the factor n in front, and then we have sum of all lattice sides. 1 over Wn plus 1, Zn minus 1. And well, this coefficient, we're going to call it Cn minus 1. And now we can notice a few things. Firstly, if n is even, then we have a sum over terms that are odd in omega or in W. But since the lattice lambda includes for every value also minus that value, we have sort of the integral over a symmetric set of an odd function. So that is 0, meaning for n even, Cn minus 1 is 0. So that if we just want the first couple of terms, we can write P of Z as 1 over Z squared plus C2Z squared plus C4Z to the 4th plus higher order terms. And that's actually all we need. Now we can have a look at what the third power looks like. And well, that looks like 1 over Z to the 6th plus 3 times C2 over Z squared plus 3 times C4, higher order terms. And if we take the derivative, and for good measure, well, that should have a Z cubed, 1 over Z cubed. So we actually wanted to have the same leading order term, so we square it. That is equal to 4 over Z to the 6th minus 8 C2 over Z squared minus 16 C4 plus higher order terms. And now we can take a linear combination of them. And in particular, can look at the derivative squared minus 4 times pz cubed, and well, also collect other terms. Can have a look at the sum. Well, first thing to note, it is elliptic because it's an algebraic combination of elliptic functions. Okay, nice. Secondly, note that, so we take the derivative squared. So we have a term of minus 4 over Z to the 6th and then we subtract 4 times 1 over z to the 6th, so those terms cancel. Then the fact that we also included this thing here means that the z squared terms also cancel. And lastly, this thing ensures that the 0 order terms also cancel. So we have an elliptic function with no poles, meaning that it has to be constant. But since all of the 0th order terms cancel, it is 0. Yeah, but is 0 at 0, hence is equal to 0. Meaning that the derivative squared is equal to 4 times the function cubed minus, and I'm going to call this term here G2 and this term G3 minus G2 times P of Z minus G3 . And notice that our G2 and G3, well, we defined them in terms of C2 and C4, and C2 and C4 are these values here that, well, only depend on the lattice, really. I mean, you can write them as some meromorphic function in omega-1 and omega-3, but really they only depend on the lattice. And if we scale that lattice, they are homogeneous in that scale, meaning that, yeah, they turn out to be modular functions, or they are what is called a modular function, and those are actually interesting in their own right. And yeah, so we have that differential equation. Nicholas, are you still there?
Yes, I'm.
Okay. So we have that differential equation, and we know that, well, there are only 3 values of p with multiplicity 2, or alternatively, the derivative just has 3 zeros, which, I mean, yeah, should be the case, since it has a pole of order 3, so it has to have 3 zeros. So omega-1, omega-2, omega-3 have multiplicity 2. We have that the derivative is 0 for those things. But what does that mean? Well, if we look at our equation above, we have 0 is equal to 4 times, and then we have eta I cubed minus G2 times eta I minus G3. So that means that the eta I, which were P of omega I, are the 3 roots of the polynomial for t cubed minus G2t minus G3, meaning that we can write this polynomial then as 4 times t minus eta 1, t minus eta 2, t minus eta 3, which then means that, well, eta 1 plus eta 2 plus eta 3 is equal to 0, and eta 1, eta 2 plus eta 2, eta 3 plus eta 3, eta 1 is equal to minus g2 over 4, and eta 1, eta 2, eta 3 is equal to g3 over 4. But I don't know, doesn't really matter. That's just some idle theorizing. Now, what is not so unimportant is the big theorem we are going to discuss now. Namely that, well, we have the Weierstrass P function and we have its derivative. And actually, every elliptic function can be expressed in terms of the two. And more concretely, it can be written as a rational function in P and its derivative. So how do we do that? Well, firstly, we can specialize a bit. Can do a lot of without loss of generality. Firstly, we split up our function f into an odd and an even function, where g is even and h is odd. I mean, we are working in a field that doesn't have characteristic 2, so everything should be fine and dandy here. But then we can actually write, well, g is even, and well, we can just multiply and divide by p prime, which, by the way, is an odd function. So we have even, and this thing over here is also even. So if we're able to express even functions, we are able to express every function. So without loss of generality, let f be even. So now the question of some value has multiplicity 1 or not is basically a question of the zeros of the derivative of f. And well, by general principles, we know that f takes almost every value with multiplicity 1. Meaning that really it is taken at a lot of different places, but with multiplicity 1. And I guess this is basically a Baire argument, but never mind. So let f of z equals c. So we say let c be one of those values for z in a1 until plus or minus ak. Note that plus or minus because it's an even function. So when it takes c 2k times on p, we can write it this way. And similarly, let's take another value that it takes, where it has sort of only, that it takes only simply for now the values b1 and so on until plus or minus bk. Then the function f minus c divided by f minus d has just simple roots and just simple poles, which, yeah, is why we did all of that. Has simple poles in, well, plus or minus a1 until plus or minus ak, and simple roots, and the same with the b's. Sorry. Should be the other way around, of course. Which is, yeah, this whole circus we only did so that our function has only simple roots and only simple poles. And now our goal is to construct a rational function in terms of a piece that has the same poles and the same roots. And then we are done, because their quotient then has no poles and no roots, therefore is constant. And what is that rational function in terms of the piece? Well, it's that function note that here we only take the product of k many terms, even though we want our function to have 2k many roots and poles. But the reason is that sort of pz minus pai, this thing has a double root, has simple roots at ai and minus ai, or if you want at ai and 2 omega 2 minus ai. So that means that their quotient has no roots and no poles, so it is a constant. And I guess the last thing to note is that you can invert this relation, but yeah. So that was the big theorem. What does that actually tell us? Well, we know that every elliptic function can be expressed as an as a rational function in terms of p and p prime. But note that p and p prime are not completely independent from each other, because we have this differential equation up here. So instead of saying that the field of elliptic functions is isomorphic to C adjoint two variables, it is actually just isomorphic to an algebraic field extension of the transcendental field extension where we adjoin P. Where S squared is equal to 4t cubed plus g2t plus g3. where we map P to T and P prime to S. Now, I don't know, we have a field extension of degree, or of transcendence degree 1. Does that somehow ring a bell, or I don't know, doesn't this whole thing remind us of something? Well, note that this thing is equal to the quotient field of, well, C, where we just adjoin S and T and then divide by the same ideal. So it is somehow equal to the field of rational functions on this thing there. So yeah, I guess that was our corollary and now remark. Those are exactly the rational functions on the algebraic curve, on the zero set, so to speak, of s squared minus 4t cubed plus g2t plus g3. And it turns out that this is the Weierstrass standard form of an elliptic curve. So I guess observation, because actually, well, remember that those G2 and G3 were actually meromorphic functions of omega 1 and omega 3, so somehow dependent on our lattice. Well, meromorphic functions are, well, not necessarily surjective, but like almost surjective. There are only very few points that meromorphic functions in general don't touch. So if we are given such a curve, we can always find a lattice such that this curve is realized. So we have some correspondence between elliptic functions and rational functions on, well, we can rescale things a bit, and then we just have z squared minus p of t, where p is a polynomial of degree 3. And yeah, I guess we also need the roots of p to be different from each other. And separable? No. P has distinct roots. And well, those are exactly going to be rational functions on elliptic curves. So what is an elliptic curve? Well, we could define it as a smooth projective curve of genus 1, nice, I guess, but that doesn't really help a lot. For our purposes, we're going to write it as the zero locus of the curve of the polynomial, well, z squared minus t cubed plus at plus b, which is called the Weierstrass normal form of that elliptic curve. And we add a point at infinity. Well, we have to, basically, because of something I'm going to mention later, where t cubed minus at minus b has non-degenerate roots, or distinct roots. Now, who's writing to me? Nothing relevant. Except now I have to find my script again. Okay. Also note, so this is should mention it maybe, this is a notion from algebraic geometry and very influential, I guess. Although usually one doesn't really consider elliptic curves over C, because one says that they are boring because they are exactly the elliptic functions which we already know about, allegedly. But anyway, I guess one thing to note is that although we have defined them as algebraic varieties, or as affine varieties even, sorry, projective varieties, we can analytify them because it's smooth. Yeah, we call elliptic curves E. E is smooth, so we can view it both as a projective variety but also as a Riemann surface. And we're going to sort of switch between those two views a couple of times. Now, one of the reasons why people are interested in elliptic curves is because they turn out to be what's called abelian varieties. So they are varieties that are also abelian groups, abelian algebraic groups. And well, one way to see this is, I guess, one exercise that I had to do for algebraic geometry once, where we had to show that for a genus 1 curve, i.e. an elliptic curve, the divisor group, sort of if we pick a distinguished point, we can establish a bijection between the curve itself and its divisor group, which is an abelian group. So then we can port the abelian group structure back and don't have to show anything like associativity, commutativity, whatever, which is very nice, but it doesn't really explain anything. So you can also just write down the group structure. That is after I've given my laptop a bit of power. Ta-da, all is bright again. So how do I explain the group law? Well, we can say that for simplicity, we look at an elliptic curve not over C but over R. Then we say that the neutral element, the neutral element is the point at infinity, and define addition as follows. Well, the curve itself looks a bit like this. Sorry. Well, it should really be symmetric across that axis, so I failed. And now if we have 2 points, A and B, then we define the addition in such a way that the points A, B, and minus A, minus B always lie on the same straight line. Well, how do we get from minus A, minus B to AB, A plus B? Well, again, recall that we sort of want we want the two summons and the negative of their sum to lie on the same line. So minus A minus B and A plus B and minus A minus B plus A plus B, 0, which is the point at infinity. They should lie on the same line. Now, where is the point at infinity actually? Well, we can view it as lying infinitely in that direction, meaning that any line that passes through the point at infinity is just a vertical line. So here, this is A plus B. Simpler way of putting this, how do we find the sum of 2 points? Well, we draw the line through them, and we find the third point where that line intersects our curve, and then we mirror it at the x-axis. This is all nice. The problem is that, well, okay, I'm going to say that after a couple of other sentences. So by this definition, we can sort of write out the group, write out some big formula for the group law. And turns out if you just interpret it as an abstract expression, it makes also sense over the complex numbers or any field really. And so this is where I guess the more cryptographic applications come in, because if you do it over a finite field or anything, then you can do wonderful cryptography with it, because you have an abelian group that is finite. So you can do like Diffie-Hellman and stuff. And it turns out to be a very well-behaved group because there aren't any well-known attacks on it. Sorry, there aren't any known attacks on it that work better than generic attacks. And also, yeah, then you have the problem of side channel attacks, because it turns out that this group law doesn't really work very nicely, because you have to work out a lot of special cases. For example, you want the point at infinity to be the neutral element, but like you can't really draw a line through the point at infinity. So you have to have a special case for that. And if you want to double a point, you have to take the tangent line, then you get another formula. So you have like 5 or 4 special cases that all take different time to compute. And this makes everything vulnerable to side channel attacks. So when the Edwards curve was introduced, that was a big deal, because the Edwards curve is another standard form for elliptic curves whose group law has just one formula. Okay, one thing to note, or I guess an interesting point, well, our elliptic curve is really a projective curve. So it is a closed subset. Well, closed in what sense? Well, firstly, it is a risky closed. But this implies that it's closed in the Euclidean topology. Subset of, well, complex projective space, two-dimensional complex projective space, which is a complex manifold, sorry, a compact set, essentially, or compact topological space. So we have a closed subset of a compact space, so it is itself compact, meaning that E is a compact abelian Lie group. Because, as I mentioned before, we can view it as a Riemann surface, so as a complex manifold, but this means we can also view it as a real manifold. And, well, the group law is algebraic, so it had better also be smooth, of dimension 2. Well, because it's one-dimensional as a complex manifold. And in the lecture on Lie groups, we had a theorem that classifies all abelian Lie groups. Namely, all abelian Lie groups have to be some number of copies of R times some torus. But since it's compact, there can be no copies of R, so it has to be isomorphic. As Lie groups to, well, R squared over Z squared, basically. Or, well, why not to C modulo lambda for some lattice lambda? Now the question is, have we maybe already found such an isomorphism? Do we know such an iso? Maybe, perhaps. And the amazing answer is yes, we do, because the Weierstrass P function has an addition identity. And I guess its derivative too. That looks exactly like the expression we used to define the addition on E. Meaning that not only is the map that sends X to, sorry, Z to P of Z and P prime of Z, which is the morphism that we use to say that sort of elliptic curves and elliptic functions are the same. That this morphism is actually a group morphism, a group homomorphism. So this thing is now the inverse of the isomorphism that we had here. And this means that, I don't know, we can sort of play a bit fast and loose here as to with elliptic functions, because we know that elliptic functions correspond to rational functions on our elliptic curve. So when we can show some equality of rational functions, we automatically have the same with elliptic functions. Or we can rescale P to get a different curve and stuff like that. And I'm going to do a bit of that now. So we start out with our equation, but already with the zeros filled in. Now what can we do? We can say that, well, this is really the same as the derivative of P of z minus eta 1 whole squared, because like constants don't add anything to the derivative. Then we have already pz minus eta 1 here. Then we can add and subtract eta 1 in the two other terms. Plus eta 1 minus eta 2 times, well, same thing. Then we can divide by this thing here squared, meaning that we get eta 2 minus eta 1 squared is equal to 4 times, and then we have, well, one of those factors we have here. Sorry, eta 2 minus eta 1. Then we have, yeah, then we take the second of our factors here, pz minus eta 1 over eta 2 minus eta 1. And here we have minus eta 2 minus eta 1, meaning that we have minus 1 essentially. And lastly, here we have, well, we're also going to do a bit of a fraction. But now we don't have any more factors of eta 2 minus eta 1, so we have to multiply again. Eta 2 minus eta 1. And, well, what we really want to is to get rid of this eta 1 minus eta 3 there. So here we have eta 3 minus eta 1 minus 1, and then we pull out a factor of eta 1 minus eta 3. Correct? No, eta 3 minus eta 1. Or if we call this fraction here g of z, this means that g prime of z squared is equal to 4 times, then we have eta 3 minus eta 1, which is just some constant, times g of z times g of z minus 1 times, and here we have some factor that we call lambda, lambda times g of z minus 1. And yeah, I guess this is a different normal form. This is called Lebesgue normal form, where instead of your zeros being eta 1, eta 2, and eta 3, the zeros are just 0, 1, and 1 over lambda. But it's just some rescaling. And some affine transformations, of course. And now we can do it go one step further. We can divide by 4 times gz, meaning that gz squared over 4 times g of z is equal to, well, still that factor of eta 3 minus eta 1 times g minus 1 times lambda g minus 1. And, well, maybe our g happens to be the square of some function. Okay, so h doesn't need to be lambda periodic. It can have some slightly weaker periodicity, but its square should equal g. I don't know why this is warranted, but this could be the case, maybe. What does that mean? Well, it means that g prime is equal to 2 times h prime. Okay, just plain arithmetic. But if we square this now, we get 4 times h squared times h prime squared. And, well, this is really equal to 4 times g, right? So then we have g prime squared over 4g is just equal to h prime squared. Which then is equal to h squared minus 1 times h lambda h squared minus 1, or 1 minus h squared, 1 minus lambda h squared. Remind you of anything yet?
You forgot the eta factor, didn't you?
Yes. Yes. Can we somehow absorb this factor? Yeah, yeah. Okay, let's do it this way. Yeah, I don't know if we can absorb this. Better not try.
We could just, without loss of generality, set this factor.
No. It is actually loss of generality.
Okay.
So I don't know. Does that remind you of anything yet? If not, we can go a bit further. So what use is this? Okay, and now I'm just going to hit you with it. Consider the integral from 0 to x of dt divided by the square root of 1 minus t squared times 1 minus lambda t squared. why not, right? For lambda being smaller than 1 and x being smaller than the square root of lambda, sorry, square root of 1 over lambda. Well, we could substitute t is equal to h of u. Why not? We have some function, we can do the substitution, and since our function h was supposed to be meromorphic, it is surjective, and if we carve out a lot of stuff, we can make it bijective. Then we have dt is equal to h prime of u du. Yes, everybody loves it when I write it like that, but shut up. What does that mean now? Now it means that we have the integral from h inverse of 0 to h inverse of x of, well, h prime of u du divided by square root of 1 minus h squared u 1 minus lambda h squared of u. But now notice that h prime is exactly equal to c times the square root of that expression, or sorry, square root of c times that expression there. So what have we? We have square root of c times the integral of h inverse 0 to h inverse of x of du. Well, modulo signs, but meaning that it is some multiple of, well, that thing here. So h is related to, well, the inverse of that integral. And what is that integral called? Say it with me. It is the incomplete elliptic integral of the first kind. So I guess it's called e(x) square root of lambda. Yeah, I think that, yeah. And, well, I guess since this is usually the first elliptic function that anyone encounters when they do physics, because like this integral pops up when you try to solve the pendulum that swings left and right, Fadenpendel. And whenever a prof says, oh no, let's not go there, this integral is elliptic, they usually mean this particular integral. So it is, from a physical standpoint, it is quite important. So it has a name. So E inverse is called Sn. And it is an example of a Jacobi elliptic function. So when you try to approach the topic of elliptic functions from a physics perspective, you usually only care about the Jacobi ones because they are related to the ones we have looked at in a nice way. But they're just physically more intuitive and also have other things. Yeah, so I'm going to do a short sketch of what these elliptic functions, these particular elliptic functions are all about, but we're not going to really dwell very much on them. The other so generally the Jacobi elliptic functions are elliptic functions that are characterized by some eccentricity parameter, which is here square root of lambda. And there are actually a lot of Jacobi elliptic functions, but the basic ones are called, well, Sn that we have already encountered, and then Cn and Dn. And the names come from, well, there are supposed to be some variations of the sine and the cosine. So Sn and Cn seem to be a bit natural. And yeah, I guess they can be calculated in terms of Jacobi theta functions, which aren't strictly elliptic functions, but they have very quickly converging power series, which is always the argument that gets the physicists. In a more general setting, yeah, you can, there's a very nice terminology. You can make up any of those elliptic functions by having the letter S, N, C, or D, and then another one of those, S, N, C, or D, with the following relations. xy times yz is equal to xz. And xx is equal to the constant 1 function. So what does that mean? Sn times nc is sc is equal to Sn over Cn, which, yeah, sure, because Nc is equal to 1 over Cn. I don't know, it's a bit goofy. Doesn't really add much value, but it's funny. And very importantly, between Sn, Cn, and Dn, we also have a few relations. Namely, we have the equivalent of the trigonometric Pythagoras, or let's say exactly the same thing. And secondly, we have another relation, which is this one. And k squared is what we called lambda before. And well, here we can see where the word elliptic comes from, because, well, this is the general equation of an ellipse. If we have an ellipse, or I guess we can parametrize an ellipse this way, because generally if we have an ellipse, the equation looks like this, is equal to 1, and then we can rescale by, or we don't really have to rescale anything. This means that x over a squared plus plus a squared over b squared times y over a squared is equal to 1. So then we can have x is equal to a times Sn u, y is equal to b times dn u, where this thing here is our k squared.
Y is also scaled with a.
Sorry, yeah. And yeah, sort of historically, one also prefers to work with these because they satisfy equations that are not third degree. Usually they are fourth degree, but with a lot of symmetry, so they are easier to handle. And yeah, also they came first because they appear as the inverse function of those elliptic integrals, which brings us naturally to the third part of this talk, namely, what the heck are elliptic integrals? And well, we haven't really, yeah, you've noticed me saying up to signs and being a bit glib about this whole business of taking square roots of complex numbers, which, I don't know, the square root of a complex number isn't actually well defined, or it involves choices. So the whole theory of elliptic integrals, I've never really liked that because they involve square roots of complex numbers and just expect you to know what it means or expect it to mean anything, which a priori it doesn't really. So, but I finally found a way to do this the proper way. And the proper way is, of course, with Riemann surfaces. So let's Fraktur R be the Riemann surface of the elliptic curve y squared is equal to p of x, where again p is some polynomial that is non-degenerate third degree polynomial. Yeah, you can already see that things are coming together now, because we're talking about elliptic curves in order to define something that should essentially be the inverse of an elliptic function. That's now normal R be a rational function on Fraktur R, a rational function now being defined in terms of viewing this thing as an elliptic curve. Any integral of the shape integral over some curve gamma of R of x and y dx is called an elliptic integral. Note that, firstly, we are working on a Riemann surface of an elliptic curve. An elliptic curve, we have seen, is isomorphic to a torus, so that Riemann surface should have non-trivial homology, meaning that integrals are in general path-dependent. So it doesn't just suffice to say the integral from some point to some other point. No, we have to specify the path. And secondly, well, we know that y squared is equal to some polynomial in x. So in a bit hand-wavy context, we can really write this as a rational function, sorry, in x, and in the square root of a polynomial in x, degree 3. But sort of with the problem of branch cuts and whatsoever taken care of. So how can we describe our favorite elliptic integrals. Let k be a number between 0 and 1. Consider the integral 0 to x dt over square root of 1 minus t squared 1 minus lambda, sorry, k squared t squared, and sort of do a bit of a process that we did before, but in reverse. Well, firstly, we can take out a factor of 1 over k. That's just from here. So we have t squared minus 1, and then t squared minus 1 over k squared. And then we can substitute t squared is equal to u, meaning that 2t dt is equal to du, or that dt is equal to du over 2 times square root of u, meaning that now we have 1 over k to 0, integral from 0 to x squared du of over, and now we have a 4 because we have this 2 there, times u minus 1 times u minus 1 over k squared. And well, we can redefine this as the integral along some curve gamma of du over v. Okay, so what are u and v now? Gamma u and v are u comma for u minus 1, u minus 1 over k squared. Okay, but now this is a curve in the Riemann surface for, well, v squared is equal to 4u u minus 1 over k squared. And you can see, by the way, we chose k, that this thing has 3 distinct roots. So yeah, we have expressed our elliptic integral as an elliptic integral. Congratulations. Also note that since we were using real numbers, and I guess we have to take x less than 1 over k squared. No, x is also less than 1. Everything is well defined, and we don't have to really make any choices, because, well, this whole expression there's positive under the root. So yes, the incomplete elliptic integral of the first kind is actually an elliptic integral. Who knew? We can do the same for the incomplete elliptic integral of the second kind. Yeah, I'm not really going to sketch a lot, but this is the integral that actually pops up if we want to calculate the arc length of an ellipse, which is what originally made the elliptic integrals elliptic. Can do a couple of substitutions here, and then we end up with 1 over k. And now we have a bit of a different integral. We had to do a bit of a different substitution because we had to get rid of this 1 minus t squared in the numerator. And here we have u minus 1 minus k squared over k squared, which we can now write as 1 over k times the integral of u du over v along the path u maps to u comma v, which is u comma, well, that square root expression here. And yeah, I guess it is a bit of a theorem that an elliptic integral can always be reduced to a linear combination of the following. Namely, the first integral we've encountered. I'm now calling them dx over y, again for no real reason, except that we use this in the definition above. Secondly, x dx over y, and thirdly, dx over x minus c times y. And, well, to keep in line with the terminology that we are used to, those are called elliptic integrals of the first kind, those are called elliptic integrals of the second kind, and those are called elliptic integrals of the third kind. The way to actually prove this theorem is really a lot of partial fraction decomposition, which is ugly as hell, but you can always find solace in the fact that you can always have that you can only have a factor of y in the denominator, because as soon as you have a factor of y squared, you can write this in terms of x's, and like you get some arctangent or whatever. So there's a proof, and then some paper which is just the worst, because it also gives like a mechanical, like it's a constructive proof that actually gives you an algorithm to calculate this, and it's an algorithm made for computer algebra systems and not for mere mortals to understand. But in the end, they reduce everything to, I guess, different elliptic integrals, but those different elliptic integrals can be turned into those. So I guess the upshot is, if you have those three functions, then you can calculate elliptic integrals. Nice, I guess. But note that, as I've previously said, those integrals are still path dependent. So you cannot expect to define them globally as a function just by fixing a base point. But we can sort of work around this a bit. We can, again, construct a lattice lambda by just saying, okay, I quotient out by the integrals along closed paths, gamma closed loop in the Riemann surface. So if you quotient out by that, then, yeah, I guess due to homology reasons, this is a lattice, meaning, well, this produces a complex number, and we have two linearly independent paths, or two cycles, two one cycles that are no one boundaries. So this forms a lattice, or like a subgroup of with two generators in C, and now the function from some base point to z dx over y is well defined as a map to C over lambda. But what is it equal to? Have we maybe already found this map? Okay, let's say that R is the elliptic curve associated with y squared is equal to 4x cubed minus g2 minus x minus g3 for some parameters. Associated, or so, yeah, the elliptic curve associated to the lattice z times 2 omega 1 direct sum z 2 omega 3, then we can lift a loop gamma on the Riemann surface to not a loop, but to a curve gamma hat on C, which is the universal cover. So we can lift things such that gamma is equal to, well, this isomorphism applied after gamma hat. And then we have the integral along gamma. Yeah, I think it should really be a curve here too. Well, sorry, here's just the y. Then we have that this is, well, what is x? X is equal to p, but we have dx, so we have the derivative of p, z dz, divided by, and y is, well, the derivative of p. Bam, they cancel. We have gamma hat of 1 minus gamma hat of 0. So what does that mean? The lattice that we've defined as the periods of that integral for closed gamma is actually equal to the lattice we had originally. And again, similarly, that function defined for some base point of that integral is actually just the inverse of p, or I guess of the morphism that maps a point to that point there. So I guess the slogan to take away is that elliptic functions are the inverses of elliptic integrals and vice versa. And elliptic functions are rational functions on elliptic curves, on complex elliptic curves. And that was it.